In section 15.2, we're going to talk about double integrals over more general regions. So in the last section, we talked about how to find the double integral over rectangles. So we want to now set up a more general double integral. We'll learn how to switch the order of integration for these more general double integrals, and then we'll recognize when a double integral represents area of these common regions. So let's kind of remember what we saw in that last section. So we had domains which were rectangles. So we thought about these regions where x went from A to B and where y went from C to D, where those were just constants. And then above that rectangular domain, we had some function f. And so we found the volume under this function f over this rectangular domain. So now we want to extend this so we can do double integrals over domains that aren't rectangles. So maybe we'll have a domain which is circular. So we'll have some nice circular domain here. And then again, above that circular domain and downstairs, right, in that xy plane, I'm still going to have some function upstairs in the positive z-axis. It could also be in the negative z-axis. And I'm going to consider the volume above that circular region in my domain below the surface given by that function f. So I'm going to have this nice volume here where, again, that top can be sort of defined by the function. I don't have to stick to sort of basic circles. I can have any shape for my domain. So maybe I have some function here that tells me the x values or the y values, a different function for the other y's at the bottom. The x's can still be between constants. That's fine. Or you can have both your x's and your y's defined by some functions. So maybe my domain space looks something like this. I can have any type of bounded region in the xy plane as my domain space, and then I'm going to have some function up above that I'm integrating. So that's the setup that we have. So let's go ahead and we're just going to try to compute one of these first. And then after we do that, we'll actually think about what we're computing. So when we have these double integrals over more general domains, the thing that we're going to notice is that the functions exist in the bounds. So instead of having my bounds that are just going between constants, I'm allowed to have functions in the bounds. And there's special rules about which type of functions you can have and where those functions can be. But let's see just first how you compute something like this. And then we'll kind of go deeper into what it's actually computing. And that'll help us understand what those rules are for what can be in the bounds. Okay, so how do I actually go ahead and compute an integral that has these bounds which are going to be functions? We're going to compute it the same way we computed our integrals where there were constants. So I'm going to do this as an iterated integral. So I can do just that first inner dy integral, where these are my y bounds. And then after that, I can do my dx integral. So let's go ahead. I'm going to keep that outer stuff the way it is. And we'll focus on just doing this inner y integral. So I'm integrating the function x, y with respect to y. If I wanted to, I could pop that x all the way out front because it doesn't depend on y, or I can leave it in either way. Let's go ahead and leave that in this example. So the x is a constant, it comes along. I integrate that y into y squared over 2. And then I need to evaluate it. This was a dy integral, so my bounds go in for y. So I'm going to go ahead and write them as y equals x squared and y equals root x, just so I remember to plug those in for my y. So we can go ahead and do that. The integral from 0 to 1. When I plug in y equals root x, I get x times root x squared over 2. And then I'm going to subtract off, plugging in y equals x squared. So x times x squared squared over 2. And then that's the function I need to integrate with respect to x. So before we do that x integral, let's go ahead and simplify that down a little bit. Root x squared is just x times that extra x becomes x squared over 2, minus x squared squared is x to the 4th times the extra x is x to the 5th. That one was also over 2. And so that's what I'm integrating with respect to x. So now I just have this nice basic dx integral with a function of x and constant bounds. So this is just like a calc 1, calc 2 integral. So we can go ahead and do that. Take the antiderivative of x squared over 2. I get x cubed over 3 times that 2 that's already there is 6, minus the antiderivative of x to the 5th is x to the 6 over 6 times that 2 that's already there is 12. And I evaluate that from 0 to 1. So I'm going to get a 6th minus a 12th, which is just a 12th. So this integral that we got was equal to 1/12. So what is that actually telling us? Well, let's think about the region that I'm integrating over. So if I go back up here and I think about my bounds, I had that the lower bound on y was x squared and the upper bound on y was root x. So I had x squared was less than or equal to y was less than or equal to root x. So that y had a lower bound of x squared and an upper bound of root x. So let's draw those functions. I'm going to go ahead and color code this here. Let's just write this root x here in this nice peach color. We'll make the x squared green. So y equals x squared. It's this guy. Y equals x squared. Nice, beautiful parabola. And then my square root function looks like this. Y equals root x. And I have that my y values have that x squared on the bottom and root x on the top. We usually think about x squared being bigger than root x, but between 0 and 1, x squared is actually on the bottom and root x is on the top. Now, if I check, my x bounds here really are 0 and 1. So I do go starting at x equals 0 and ending at x equals 1. So the domain, the region that I'm integrating over, is this nice region stuck here between y equals x squared and y equals root x. So that's that region that I'm integrating over. So in 3D, what this is going to look like is I'm going to have my function x times y. So that's going to be, some sort of function that's kind of sticking up like this, coming out here. Who knows what's going to look like. That's in 3D. And then down, I'm going to have my x squared and my root x down there in the xy plane. So that's going to give me my sort of bottom here. And then the function is going to kind of come up. So I'll say maybe go straight up to some function up here. And I'll see also that green and peach area up here. And I'm going to get some volume above that. So that's that basic shape that we're going to see. Let me go ahead and pull in a nice picture from GeoGebra and we can talk through that one more time. So let's look real quickly and see what we have here, what we're actually computing. So what I've sketched so far, the graph here is that z equals x times y. So it's that nice, looks kind of like a Pringle chip shape. And now we've put in this green line y equals x squared down there in the domain. So that's that nice y equals x squared curve there, that green one. And now we've also got that orange or peach colored y equals square root of x. So we can see that region in the domain space between x squared and root x. And now what we want to do is we want to look at the volume above that region below that surface x times y, that red surface. So let's see if we can sort of picture that better. So I've put that curve now, that y equals x squared curve, I've just sort of lifted it up so it goes all the way up to the surface. And we can do the same thing with that y equals square root of x curve. Now we can put in those surfaces, those walls. So now that's the region that I'm trying to find this volume of. So it's above that y equals x squared and y equals root x, below the surface xy. So now I've put in that ceiling there, and we can see now in 3D exactly this shape that we're trying to find the volume of. So that's what we calculated. The volume of that region there was that 1/12. So that's what's going on here. All right, so let's get this out of the way just so that you can go back and look at it later. and then we can move on and look at some other examples. Okay, so let's go ahead and evaluate this integral. So I've got the integral from 0 to 8 and from cube root of y to 2. And I want to integrate the function e to the x to the fourth. Now, one of the things that you need to do is you need to recognize that this e to the x to the fourth function is not a function that we can actually integrate. So this is not a function that has a nice algebraic antiderivative that we can write down. It's going to be helpful if you remember some of these functions that are going to be impossible. So in particular, you should recognize if you just have an e to the x squared without that x in front of it. Remember we saw if we had the x in front of it, we could do a substitution. But without the x in front of it, that's going to be impossible to integrate. E to the x to the fourth is another one. And then we'll also see cosine x squared and sine x squared. So anytime you see those, you should be like, okay, this is something that's impossible. We need to make sure we find another way to do it. And that's what switching the order of integration is going to allow us to do. So let's think about what we're actually trying to integrate in this. So what is the region that we're trying to integrate? So what do I have? I have x equals cube root of y to x equals 2. So if I think about that, my x goes between the cube root of y and 2. And then the y, we can look at those y bounds as well. So the y goes from 0 to 8. So let's go ahead and sketch that domain of integration. The domains are just going to be sketched in the xy plane, so we're not needing to sketch anything in 3D. I have x equals the cube root of y, which I can change, cubing both sides, into y equals x cubed. And so I know y equals x cubed, like something like this. And then I have x equals 2. So x equals 2, we go to 2 on the x-axis, and we have that curve x equals 2. So I have x equals 2, and x equals cube root of y, which we said is the same as y equals x cubed. And now those are my x bounds. So x is in between here. On the one side, the lower values of x are that cube root of y, and the bigger values are that 2. So this region here is my domain of integration. So what we can do is we can try to rewrite this so that we have the y first instead of the x first. And that's going to allow us to actually be able to do this integral. So let's go ahead and pop into the next page just so that we can do that. So I'm going to bring this picture with me, and we'll go ahead and copy that so that we have it with us. Okay, so again, I'm going to try to evaluate this function here, but now I'm going to do it by changing that order of integration. So again, let's think about that region that we were trying to integrate. This was that region that we had here. And so what I'm going to do is I'm going to change this. So instead of having an x first integral, I'm going to have a y first integral. So we have a very specific way that we want to think about these. I'm just going to keep everything color-coded. For my y first integral, I want to move in the direction of the y-axis. And I want to think about the sort of smallest y values that we have to those biggest y values. Now, as I'm doing this, always the innermost thing, I want to think about those bounds being curves. So some sort of function or expression. I'm not just thinking about a constant, I'm thinking about a curve. And then the next step out, those should be constants. Okay, so what am I doing? I'm moving in the direction of the y-axis. So the y-axis is up and down, so I'm moving in the direction of the y-axis from the smallest y values to the biggest y values. So I'm moving up, and the first thing I hit is this bottom curve here. So I need to figure out what that curve is, that entire line, as a y equals some function. And then I move up, and the next thing I hit is this curve here. So again, I'm looking for curves that I'm hitting. I'm not looking for just numbers, and I need to write that curve as a y equals. So this bottom curve down here, that's y equals 0, because for every point along that curve, y equals 0. This top curve, again, right, it's not just a constant value. It's not always equal to 0. It's not always equal to 1. It changes. And that we said was going to be y equals x cubed. So my y values are going to go from 0 to x cubed. The function stays the same, so we leave that as e to the x to the 4th. And then the x values, now those are just constants. So I just look for constants along the x-axis to figure out the smallest number and the biggest number. So the first inside is curves, but the outside is constants. Curves, then constants. Okay, so I switched it. So now it goes from 0 to x cubed of e to the x4th dy, and then 0 to 2 for dx. So if I just rewrite this integral so that we can actually see if we can do it now, I still have to integrate e to the x to the 4th, but now I have to integrate that dy instead of dx, and it's a constant with respect to y, so it's going to be easy to integrate. So I get 0 to 2 dx, that was my x integrals, that just stays outside. Inside I integrate e to the x to the 4th is just a constant, integrate it with respect to y, so I just get y in there from 0 to, oh, what did I write? I wrote it 2 here, but I should have written that x to the 4th, because that's what I had up there. X cubed, sorry. X cubed, great. All right, back up to it. 0 to 2, these are my y bounds, remember? So I plug it in for y. So I end up with x cubed e to the x to the 4th minus 0. And now I'm really in great shape because I still have to integrate with respect to x here, but I've got this extra x cubed out front. So that's going to allow me to do the substitution that I need to do to integrate e to the x to the 4th. So I'll let my u be x to the 4th. My du is 4x cubed dx. So my x cubed dx can become a du over 4. And I get the integral. I'm going to leave my bounds in terms of x. I don't feel like changing them. X equals e to the u du over 4. So I end up with 1/4 e to the u. Let's go ahead and just plug that back in. E to the x to the 4th, evaluated from 0 to 2. So I get 1/4 e 2, 4, 8, 16. E to the 16th minus e to the 0 is 1. So I just get 1/4 e to the 16th minus 1/4. So by changing the order of integration, we're going to allow ourselves to compute these integrals, which would be impossible to compute if we didn't change that order of integration. So that's really helpful for us. So we do have to be careful when we're switching the order of integration. Remember before when we had rectangles, we could just change those bounds around without really thinking. But now, again, remember we said we're going to have these curves on the inside. That's good. We like to have curves with an x as long as there's a dx after. So I'm allowed to have x in my bounds if there's an x later. Because when I integrate this, what's going to happen sort of in general, I'm going to integrate with respect to y. And then I'm going to replace the y with either g1 of x or g2 of x. So I get rid of all of the y's. And then I integrate something with x's with respect to x, and then plug in x equals a and x equals b, and just get some sort of constant. So I am going to get this nice constant at the end. I'm sort of able to get rid of both of my variables. Now, if I did this the other way, let me actually put my dx and dy in here. If we think about just switching it without really thinking, I integrate this with respect to x. So I get rid of x and replace with constants. That's still fine. Now I have no x's left. But then I have the integral g1 of x, g2 of x, of some function with y dy. So if I think about doing that, well, this is going to make me replace, after I take the antiderivative, the y's with x's. So I still have x's at the end. And I definitely don't want that. I don't want to end up with having a function of x. I want to end up with a constant. So I can't just switch the order of integrations. I can't have x's in the bounds after I've already integrated with respect to x. I can only have those before I integrate with respect to x. So that's something helpful to kind of keep in mind as we're going through these examples. All right, so let's look at another example where we switch the order of integration. And again, right, we're not going to just switch these around. We're going to actually have to think about the region that we're integrating over, and then we're going to go ahead and switch that. I'm going to do it graphically because I feel like that's the best approach. But after I do that, I'll sort of show you a little bit of how you can do it algebraically. Now, be careful because that algebraic approach can get kind of sketchy for some of the other examples we're going to do. The graphical approach always is going to work out really nicely if you can graph these functions. So what is my region of integration going to look like? It goes from y equals 0. So remember, inside is always curves, outside is always constants. So the curve y equals 0, that's going to be this entire x-axis. And then I'm going to go to the curve y equals 2x. So this is my curve y equals 2x. Lines are special cases of curves. And then I'm going to think constants here. X equals 0 and x equals 2. So I'm going to fill those in just as points. And then we can say, okay, we have to kind of fill in between x equals 0 and x equals 2, the region where the y's have y equals 0 at the bottom and y equals 2x at the top. So I have that y equals 0 and that y equals 2x up at the top here. So this is the region where y has 0 on the bottom, 2x on the top, and then x goes from 0 to 2. So that's that nice region I'm integrating. So if I want to switch it to the other order, we'll just get our basic setup here. I'm going to do a dx first and then a dy. The function stays exactly the same. And so now I want to do x first. So I want to move in the direction of the x-axis from smaller values to bigger. And then I'm going to look for the innermost thing for the curve that you start with and then the curve that you end with. So here's my x-axis. It goes in this direction horizontally. So I'm moving in the direction of that x-axis. The first thing I hit when I'm moving there, the first thing I hit is this blue curve here. And then the second thing, right, keep moving, keep moving. Think about where you're leaving. The curve in which you're leaving is this curve here. So now I just need to write those both as x equals curves. So if it's dx, we're looking for x equals something. So this one I know is y equals 2x, so I can solve for x equals y over 2. This one is x equals 2 as a curve. So I'm going from x equals y over 2 to x equals 2. And now I just have to look for constants for my y. So the lowest value that we had hit on that y-axis is y equals 0. The highest value is whatever y value corresponds to this. I know x is 2. Y is just 2 times that x. So that y is going to be 4. So I've got my constants for y, and I've got my curves for x. Okay, so again, that's the nice graphical approach. Always works, definitely what I recommend. Some people prefer to do this algebraically, so let me show you what that might look like. When I do it algebraically, I'm going to view these bounds as sort of inequalities. So I have y to start out, and it goes from that 0 on the bottom to 2x on the top. And then I have x going from 0 to 2. And so the way I like to think about this is I want to change these inequalities from this y perspective to an x perspective. So I'm going to try to get them to all just be about x instead of being about y. So I want to get the x's to it by itself. So change to some sort of x perspective. Okay, so the second one's already about x. So the first one I just have to change. So I'm going to divide everything by 2 so I can get that x by itself. So I get 0 is less than or equal to y over 2 is less than or equal to x. And now I'm going to combine that with my other inequality. So let me just kind of go down here. So I had that 0 already. Now I know there's a y over 2 in there. And then I have the x, and then I just have that upper bound of 2 for my x. Okay, so now that we have this, we have everything in terms of just a single x, and I put it all in one inequality. So I can look at the thing right below x and the thing right above x, and that'll give me my x bounds. So x goes from y over 2 to 2. Now I'm going to rewrite that inequality without the x in there. And then solve that new inequality for y, because I already figured out what my x bounds were. And that will give me that y goes from 0 to 4. So that's an algebraic way you can do it. You can get all the inequalities in terms of your new inside variable, look at the lowest thing and the highest thing, and then get rid of that and look what's left. So that's, again, an algebraic approach that will sometimes work, but I definitely think it's better to take this and look at this geometrically, and it'll be helpful you later in the course when we get into triple integrals. Okay, so there are 2 different types of these general regions that we're going to see. So one of them is called type y. And the way that we can think about these type y integrals, that just means that we can set it up. We don't have to, but we can set it up. We can set up by doing a y integral first. So if it's type y, that means you can do y first. So the x's are going to be going between constants. So some nice constant a and some constant b. And then the y will just have some function. I'll call this maybe t of x for the top and b of x for the bottom and top. So the y goes from that bottom function of x to the top function of x. So again, we should think of these as y equals functions if I'm doing the y first. And so if I wanted to set up my integral as a type y, I do y first, and then after that I do x. Then I would just say that my y goes from that b of x to t of x. So I put the b of x on the bottom and the t of x on the top. And then the x, we can see, just goes from that a to b. A to b, and so we keep the function in there, f of xy. So if I have a type y, we can set up as y first, just like this. So we have that y equals function on the bottom, that y equals function on the top. We're allowed to have x's in those bounds, because after that, we integrate with respect to x. We have the same thing, or a similar thing, for a type integral. So for type x, we want to think about having some function here on the lower side, so that left side of x, a different function on the bigger side of x, and these are going to be x equals functions. So again, I'm going to call this like r of x because it's the right side. We'll call this one L of x. Sorry, L of y. It's x equals has to be a function of y. So I have r of y and some L of y. And so the x goes from some left function to some right function. And those are x equals functions because it's all x focused here. And if it's an x equals function, then it should have y's inside of it. And then the y's are just going to be going from some constants. So we can call those, again, just a and b. So I've got a there on the bottom. And then I'll just put my b on the top. So y goes from that a to that b. So I've got y equals a on the bottom and then b on the top. So again, if I'm going to set up that integral, I'm going to have f of x, y. I'm doing a type x, so that means I'm going to do x first. So type x just means we can set up doing x first. So x goes from that left side to that right side. These are x equals functions because it's x focused and it has to be a function of y. And then after that, we're going to do our y's. And the y goes from the a to the b. And I am allowed to have y's here because afterwards I'm going to integrate with respect to y. So we can set up these integrals in either order depending on the function. All right, let's do one more example of switching the order of integration here. I'm going to go ahead and do the same thing. I'm going to look at this graphically. So I've got x equals 0 and x equals 4 minus y squared square rooted as my x equals curves. So x equals 0 is going to be that y-axis. So I'm thinking of this as the curve, x equals 0. And then if I have x equals the square root of 4 minus y squared, maybe it's sometimes hard to picture what this is, but if we square both sides and add that y squared over, we should be able to go ahead and recognize that this is a circle of radius 2. Now, because it was written as a square root with only the plus there, that means I only have the positive x parts of this circle. So I have a circle of radius 2, but only the parts where x was positive. So I have that circle, radius 2, when the x values were positive. So that's what I have so far for my curves for x. Now let's check those y values. Y is going to go from -2 to 2. So there's my constants on the y-axis. So I do get this entire half of the circle where x was positive. Now we can go ahead and set that up as a y equals integral. So I'm going to again have my function of x and y. I'll have the y equals on the inside and the x equals on the outside. I'm doing a y first integral, so I'm moving in the direction of the y-axis. I want to think about what the bottom curve that I'm hitting is. So it's the bottom of this circle. And then I want to think about the top curve that I'm hitting, which is the top of this circle. So as a function of y, I should be able to get two different curves. I should be able to get the bottom half as one of them and the top half as the other. So I have sort of this bottom part of my circle that's going to need to go down here. And then I'm going to have this top part of the circle that's going to have to go up here. So we need to figure out what those are in terms of y equals. So again, remember the circle equation came from this x equals the square root of 4 minus y squared. So we already squared both sides to get that x squared plus y squared equals 4. So y squared is 4 minus x squared, which means y is plus or minus, where we do get the plus and the minus here, square root of 4 minus x squared. So the bottom is coming from that negative square root of 4 minus x squared, and the top is coming from that positive square root of 4 minus x squared. So I'm going to get on the bottom negative square root 4 minus x squared, and then on the top square root of 4 minus x squared. So we do have that circle on both the top and the bottom. Now for x, I'm just looking for constants. So I see that I start at x equals 0 and I end at x equals 2. So this is going to be the setup in that other order. So again, if you draw these out, you look at the pictures, you solve the equations for those curves in the other direction, then that should help you set these up. All right, I've got one last question here. This was set up so you can kind of answer in a poll, but I'm going to go ahead and we can just vote, decide for each of these if it's type X or type Y, both or neither. So I want to ask myself, if I try to set this up as an X first or a Y first, can I do that with only one integral? So for the first one, if I try to do type X, if I try to move in the direction of the x-axis, sometimes the first thing I hit is going to be this pink curve, and other times the first thing I hit is going to be that purple curve. And so that's not going to be good for us. We're not going to like to set that up because I don't just have one curve that I'm hitting when I'm moving in the x direction. So it's not type X, so it can't be both. So either it's type Y or neither. But if I go in the direction of the y-axis now, if I'm moving bottom to top, the first thing I hit for the y, the lower bound is always this nice purple curve, and the upper bound is always the pink curve. So I can set this up as a y first integral because I can just go from whatever the purple curve is to whatever the pink curve is. I always have purple on the bottom and pink on the top, so that is going to be type X. All right, now let's look at our next region here. For this one, if I try to move in the direction of the x-axis, I'm moving left to right here, I always hit that purple curve first, and then I always hit that green curve second. So if I were to set up this integral, on the bottom, I would go purple. Let me write purple and purple. Purple. And on the top, I'm going to hit green. So the smallest x is always purple. The biggest x is always green. So that's going to be my dx. That's going to work. And then dy would just have on the bottom that peach, whatever that number is, right? That's a set number because it's a nice straight curve. And then whatever that top is would go here. So that does work for type X. But if I try to do type Y, I'm moving bottom to top. I do see always peach on the bottom. That's great. But then as I'm going to leave this surface, I'm going to have purple on one side, but green on the other. So if I tried to set it up as type Y, I would actually have to use two different integrals. One would go from peach to purple, and the other would go from peach to green, depending on where you are. And so since it's going to require me to use two different integrals, I could still set it up. It's not completely impossible, but we don't call that type Y because it requires two integrals. So it's not type Y. So it's not both. It's not neither. In this case, this one was only type X, and above was only type Y. All right, last thing for now, we just want to talk about what we get when we integrate 1. So just like before, we can think about having, right, our nice set region here. I'm integrating the function 1, so it's going to give me a height of 1. So the volume here is just going to equal whatever that base area is times the height. But here, that height is always just going to be 1 because the function I'm integrating is 1. So I am just going to get that nice base area. So when I'm integrating the function 1, I do get area of D, the area of that domain. So that's really important to remember. So sometimes they can give us these integrals of the function 1, and we can just recognize, oh, this should be the area of that region. And so if we can recognize what that region looks like, oh, look, I've got y equals positive and negative square roots. I remember that from the last example. That's just going to give me this circle of radius 3. I do have both the negative y's and the positive y's. And I've got the negative x's and the positive x's. So I'm going to get the entire circle here. This just gives me the area of that circle. But the area of a circle is just pi times the radius squared. So I don't even need to do out that integral because I can just recognize that it's an area. Now, the only reason it was an area is because we had this 1 inside. If there was another function in there that wasn't 1, then we wouldn't get area, and we would actually have to do out the integral. But if the function is just 1, then you're just getting the area of that region. So if you happen to know some geometry to help you find the area of that region, then you don't have to do out the integral. So that's really important to remember. There's a couple more examples in here on setting up some more complicated regions. I have a separate video on those, so if you want to just go and check out that video, you can, or you can always try the examples on your own first and then watch the video later. But be sure to check that out. If you're struggling with sketching these regions, because it's been a while since you sketched the function, there's also another bonus video on practicing sketching different regions. So again, check out those if you need to see some more examples, either of sketching or of just setting these up. And I'm happy to answer any questions you have, so please let me know whatever those questions are. That's all for now.